Hello, my dear students, and this time I'm coming to you with a microphone on and want to talk to you about the final material in our chapter 4, Reactions and Aqueous Solutions. And as part of this final slide in our brief discussion on oxidation reduction reactions, there was a picture inappropriately placed where I start with a 1 molar stock solution. Uh-oh, what the heck is that? And I take 25 mils of it with a very accurate volumetric TD pipette, to deliver pipette, and I put it into a 250 milliliter volumetric flask and very carefully add to the calibration mark, which is calibrated even for a specific room temperature, and mix to create a dilute solution. The question is, what concentration is it? Well, that's what I want to talk about, is some aspects of solution stoichiometry. So I'll continue in my Ridge Runner Red Solution Stoichiometry. Stoichiometry involves numbers, but remember, we're just balancing things out and watching our numbers. So we have this new concept, not moles, but molarity. And molarity is the number of moles in a given volume, typically moles and liters. That's not always useful, especially in my field, so we have terms like millimolar and micromolar. But molarity is abbreviated Big M. Okay? And the amount dissolved is concentration. There are other ways to do concentration. Weight volume, 10 grams per liter. Okay? Weight, 10 grams per 100 grams of water. There is percentages, although is the percent based on weight or volume, as long as you define it. But the one thing that simplifies everything for me is always is the mole concept. Always go through the mole. Moles help. And molarity is maybe not the easiest, but it's the most straightforward and most assured way to represent concentration. It's a measure of the concentration of a solution, how much solute in moles is dissolved per liter. And usually we're talking about a liter of water because, especially in this chapter, we're talking aqueous solutions. So, if I wanted to make a known molarity of a solution, if I wanted to make a 1 molar solution, I would weigh out 1 mole of that material and put it into a 1 liter flask. We're using volumetric flasks here to make a 1 molar solution. 1 mole per liter, right? 1 mole per 1 liter is a 1 molar solution. Now look at this example. I'm going to enlarge it. Oops. I'm going to enlarge it. And if I weigh out 1/4 of a mole of copper sulfate, about 40 grams, its molar mass is about 160 or 159.6. But if I weigh out 39.9 grams of copper sulfate, that is 1/4 of a mole. Okay? How did I do that? I'll show you in a minute. And I put that 1/4 of a mole into 1/4 of a liter, or 250 milliliters. I will make a 1 molar solution. Pretty blue solution. So when I weighed out 39, as they say here, 0.9 grams of copper sulfate, What I needed was my formula weight, or molar mass, or molecular weight, however you want to say it. I'm old, I say molecular weight. I'm supposed to really say formula mass or formula weight because we're talking about an ionic compound. That's a WT. Let me go back and fix that and make it neater. Formula weight. And into a known volume of water, put some water in there, dissolve it completely, and then slowly bring it up to the line, wherever the line is. I guess it's down there. In these very accurate volumetric, and moderately expensive, by the way, volumetric flasks. So, that's how we make it in the lab. The other thing you can do is, if you look around in my lab, you'll see concentrated solutions, because I don't like making up this solution all the time. I make a lot of a more concentrated solution. You can tell it's more concentrated with this copper sulfate, because the more concentrated it is, the darker blue it is, okay? And then if you dilute it out, of course, you're diluting out that color. But one way you can make a solution is to start with a more concentrated solution. Because water is plentiful and water is everywhere, and this happens in industry, all kinds of places. At McDonald's, they don't buy millions of gallons of Coke. They buy fewer millions of gallons of Coke concentrate and highly carbonated water, and they mix them to get the right flavor, sugar, and carbonation balance. So they start with more concentrated solutions to make weaker solutions so that they don't have to pay to transport water, because water is available at each endpoint, at each service point. So they don't go into a lab and do it like the process is here, but one way, if this is a 10x, for example, 2 point, let's say 10 molar solution, and I want a 1 molar, 1.0 molar solution, and again, 1.0 big M. Big M means moles per liter, or molar solution. Then one thing I can do is take, for example, 25 mils of this and put it into a total of 250 mils of water. In other words, mix 25 mils of this dark blue solution with 225 mils of water. You have to be careful, because sometimes you need to account for something called specific volume, and sometimes when you mix two solutions, 25 mils of one and 25 mils of the other, you don't automatically get 50 mils. So there are some important considerations in the practical application, especially in quantitative chemistry, analytical chemistry, where you're interested in very precise values. One way I can do this is to do what I use as M1V1 equals M2V2. Okay? The molarity, or concentration of one, times the volume of one solution is equal to the molarity and concentration of the two. It doesn't matter who's more concentrated or which is which. Your book uses concentrated and dilute. But let's take the example we just used. It had a 1 molar amount, or 1 molar concentration, and a volume of, and I can stay in mils if you want to know the truth, a volume of 25 milliliters. You could say 0.025 liters, if you want to stay in liters. but these values are going to cancel out, is equal to, what's my final concentration there? I don't know. But I know my final volume was 250 milliliters. So when you use M1V1 equals M2V2, it's the molarity of the first solution times its volume is equal to the molarity of the second solution times the second volume. And you can work forward and backwards. You can use both, when you do this, you can use both, like I say, you can go in either directions, and you can use liters or milliliters as long as your units are the same. And when you do this, if I solve, cross multiply and solve or whatever, I get 1 times 25 divided by 250, which is equal to 0.1 molar. And that's my new concentration. If I know how much of the original I took and its concentration, and I know what volume I ended up with, I can calculate my final concentration. I'll only give you one problem like that. The other thing is that's using and starting with my concentrations, but you don't always know your molarities. But if you know your molarities, you can calculate how many moles you have. I'll show you this in the problem-solving set. I have just a couple of problems dealing with this, and we're going to convert from molarity to how many moles of substance is there, or we're going to go the other direction and say I have this many moles in this volume, and we're going to calculate molarity. If I know how many moles I have, whatever it is, I can calculate its mass as well using its formula weight. We'll practice that. There's a process called titration, which you should know. We should do an experiment with it, but this being an online course, we'll be watching it or just describing it. But in titration, you slowly add a volume to a known quantity, or an unknown quantity you add a known volume of known concentration to. It doesn't matter. You have to know one or the other. And from your volumes, when you, for example, in an acid neutralization reaction, if you start with an acid, fruit juice, Coca-Cola, any of those, and you have an indicator that tells you when you reach neutrality, in this case it's phenolphthalein, something that goes from colorless to pink at pH 7 at neutrality, you add a standard sodium hydroxide solution to your acid. You can make highly accurate standard solutions of sodium hydroxide, especially if you titrate them and standardize them. Then you can, from how much sodium hydroxide you added, tell how acidic this was. And once you reach pH 7, you knew what volume it took you to reach that, so you can go back to calculate the original pH and from there the concentration, because remember, pH is what? A value related to the concentration. It's minus a log of the hydrogen concentration. So when you do a titration, if I ask you a question on a test, it'll just be more definition for now. A standard solution is used, and you can use a standard solution in your flask, or you can use it in what we call your burette, which, oops, I'm not lining up very well, has a petcock that controls the drips out of the burette into the solution in the flask. But that being said, one of them must be standardized, must be standard. You can titrate with the standard, or you can titrate into the standard if you have a known amount here. But what we need are known amounts so that we can use our V1 M1 equals V2 M2, because we'll know with assuredness the molarity of our standard solution, and we'll know what volume we used, whether it's the amount we added, because we're measuring in this burette. This is a very accurate measuring device for measuring volumes of liquids, or we know what volume we added here. We added 25 mils, 250 mils. So we know our volume, we know our molarity of our standard solution. We don't know the concentration of the unknown solution, but we can either know whether it's up here or down here. We can either know how much we added to neutralize and reach an equivalence point, or we can know how much we added down here. So we know our volume. What we can find out is our unknown molarity using our equation. You can use this with acid-base reactions. You can use this with oxidation reduction reactions, because we have a lot of indicators that change color depending on whether or not they're reduced or oxidized. So when something is completely oxidized up and ready to oxidize something else or reduce something, or something else get reduced, we can have a color change with one of those indicators at the equivalence point. I believe that's it. Check out the problems, and I will have additional explanation on how to use this information in the world